Hello, my name is Mad Max. In the last episode, we talked about the formation of our solar system and what is called cosmochemical differentiation. Differentiation sounds complicated, but it's pretty easy. It just means that you separate substances with different properties by their properties. In case of the cosmochemical differentiation, it means that we have rock planets close to the Sun, gas planets far away from the Sun. Why? Watch my last episode. I want to talk a little bit more about the formation and about the history of the Earth, but to do this we need certain tools to understand it, and one of those tools is radiometric dating. So this episode will be about radiometric dating. What do I mean by radiometric dating and how does it work? Well, let's say you have popcorn kernels, okay? You have corn kernels and you want to make popcorn. You put a couple of those kernels, let's say 10, in a pan and you wait. It's impossible for you to tell which kernel will pop first because they are popping randomly, okay? But if we would make a graph, this number over time. Alright, so time number. It's very easy. We have time here. This is number, okay? Those are unpopped kernels, those are popped kernels. We start with 0 popped kernels and let's say 100 unpopped kernels, okay? First of all, lots and lots and lots of kernels pop. Because there are a lot of unpopped kernels, a lot of kernels pop. But the number of unpopped kernels goes down and down and down and down and down. So the speed at which this curve goes up goes down too, because there aren't that many kernels left, right? At this point right here, there is only a really low number of unpopped kernels left. So there aren't that many kernels that pop anymore. So this process is random, right? Well, yeah, it is. But in all of this randomness, right, in this chaos, again, there is something constant. And this something that is constant is what is called half-life. The half-life of our popcorn is the time it takes for half of the kernels to pop. Okay? So if you start with 100, one half-life would be this time right here. This time at which half of the kernels are popped. This is the half-life. This is the half-life of our popcorn. And interestingly enough, the time it takes to get from 100 to 50 kernels, right? The time it takes to get from 100 to 50 kernels, from here to here, is exactly the time it takes to get from, wait for it, from 50 to 25 kernels. Okay? This time right here, that it takes from 100 to 50 kernels is exactly the same as this time right here, that it takes to get from 50 to 25 kernels. And this time right here is the time that it takes to get from 25 to 12 kernels, and so on. This time is called the half-life of our popcorn. Okay? Now, why am I talking about popcorn? Well, let's make a little thought experiment. Let's say we put a bag with 100 kernels into a microwave. We obviously start the microwave, right? We leave the room, and when we come back an hour later, we find out that the microwave doesn't work anymore. So at some time between us leaving the room and us coming back into the room, the microwave stopped working. Now, the question is there a way for us to find out how long the microwave has been working? And yes, there is. We can use this to find out how long the microwave was actually working. And what we will do is we will just count the number of popped kernels. Okay? Or let's count the number of unpopped kernels, okay? If we find 50 unpopped kernels, we know, 50 kernels popped. That's exactly the half of 100 kernels, so that's one half-life. Right? Let's say the half-life is 5 minutes. Let's give it a number, okay? Let's say the half-life is 5 minutes. If we have only 25 unpopped kernels left, we know, 10 minutes, 2 half-lives. So this way, only by knowing this constant, this half-life, and by counting how many kernels popped versus how many aren't popped, we know how long the microwave has been working. We know how long the microwave has been popping popcorn. Pretty simple, right? Now, it's important here to note that you do not necessarily need to know how many popcorn kernels you had to begin with. Because what you can do is you can just look at this, right? And you can count, okay, I have 25 unpopped kernels and I have 75 popped kernels. That's a total of 100. So 75% of my kernels popped, and you can use that to calculate how long it took, how long the microwave was working. Now, one thing that's important to note is that this method only works if you do not interfere with the popcorn popping process. If, while the microwave is on, you would remove popped kernels, or you would add fresh unpopped kernels, this wouldn't work anymore. Right? Because you are removing popped kernels. So the number of popped kernels is different from what it would be. So all your calculations don't work anymore. There's another problem with this method. Let's say we grow tired of counting everything by hand, because, you know, it takes a long time. Let's say, where is my black? Oh, yeah. Let's say one kernel equals 1 gram, okay? Let's say the mass of one kernel is 1 gram. And let's just put the stuff on a scale, okay? We just open the bag slightly, we get rid of all the unpopped kernels, and we put the rest of the bag on the scale. And then we know, okay, well, we have 50 gram, that's about 50 kernels. That's cool, right? The problem is that every measurement, every bit of measuring equipment has a certain error. Every bit of measuring equipment has a certain error. Every measurement has an error. So, if I would, for example, take this yardstick, right? It's cheap. I cannot remember that I ever paid for a yardstick. They just kind of pop into existence, I guess. But it has a pretty high error, because the best you can do is like 1 millimeter. If I would try to measure 0.5 millimeter with that, I would need to guess what 0.5 millimeter is, right? So the error would be pretty high. The error in this case is maybe 0.5 millimeter, whereas this digital caliper right here has a lower error, right? But it has an error. If I zero it, oh, it needs a new battery, I think. If I zero it and I open and close it a couple times, I hope you can see that. If I open and close it a couple times, okay, you see it's now says 0.02 millimeters. Why? I zeroed it, then I opened and closed it a couple times. I do it again. I zero it and just open and close it a couple times. Now it's minus, come on. Now it's minus 0.02 millimeters. Why? Well, that is the error of this piece of equipment. The error of this caliper is 0.02 millimeters. So if I would do science, right, if I want to publish how thick this yardstick is, right, I would measure it. Now I have 2.8 millimeters, right, 2.80 millimeters. So what I would publish is 2.8 millimeters plus minus 0.02 millimeters, because that's the error. Okay, scientists take this very seriously. Scientists always publish the error together with their values. If you only publish the values, it's meaningless, because you can't judge how good the numbers are if you don't know how big the error is. Okay, so every bit of measurement equipment has an error. Let's say the error of our scale is 1 gram, plus minus 1 gram. Alright? So, what does this mean for this? If we wait 5 minutes, we have 50 popped kernels, okay? That's 50 grams. 1 gram of 50 grams, that's 2% error, okay? After 2 half-lives, we only measure 25 unpopped kernels, okay? So 1 gram of 25 grams, that's 4% error. If we wait another half-life, we have 1 over 12. That's 8% error. And after 4 half-lives, we are at 16% error. So the relative error doubles every single half-life. So the longer we wait, the worse our measurement gets, the higher the relative error gets. That's a problem with this method. How do we get around this problem? Well, first, let's quickly recap, okay? We put a certain number of popcorn kernels into our microwave. They pop randomly, but the number at which half of them pop is a constant. It's called the half-life. And just by knowing the half-life, we can calculate how long the microwave must have worked, how long the microwave has popped popcorn kernels. However, due to measurement errors, right, the longer we wait and the smaller this number gets, the higher the relative error is. And since scientists don't like high relative errors, they would only use this method to maybe 3 half-lives, which in this case is 15 minutes. Now, let's say we add another kind of corn, or we use another kind of corn. This different kind of corn has a different half-life. This different kind of corn has a half-life of about 20 minutes. Alright. This was our old popcorn, half-life 5 minutes. This is our new popcorn, half-life is 20 minutes, okay? So it has a way longer half-life. So that means suddenly we can use this new corn to measure longer time frames. Because this showed us that we can use this to measure about 3 half-lives, right? And 3 half-lives with our original corn is 15 minutes. But 3 half-lives with our new corn is 60 minutes. So by using a different kind of corn with a different half-life, we can now measure for longer times. We can date the age of our popcorn, or we can measure how long the microwave popped for longer periods of time. There's a trade-off, however, and this trade-off is that for very short time frames, let's say like 1 minute, this new corn doesn't work that well, because it has such a long half-life. Then in 1 minute you do not get a lot of popped corns, and then again, because you don't have a lot of popped corns, your measurement error would be pretty high. So what ends up happening is that you have time intervals at which different half-lives work well. Excuse me. So for our half-life of 5 minutes, we can measure everything between, let's say, 3 minutes and 15 minutes. Whereas with our 20-minute half-life, we can measure everything between, let's say, 7 minutes. I actually calculated that. And 60 minutes. Okay, this is popcorn kernel number 1. That's good in this time frame. And this is popcorn kernel number 2. That is good in another time frame, because there's another half-life. Now there's an area where they overlap. There's an area where they overlap, like this. So if you would take 2 measurements, and one measurement is here, right, and the other measurement is here, then we can be pretty confident that this is the right time, because 2 different kinds of corn got us the same time. Not exactly the same time, you have error, you have always error, but it's about the same time. So the more different kinds of corn you use to do this, the higher your precision gets, and the more you can trust your result, right? Now, all I just told you holds true for radioactive decay too. Every radioactive isotope has a certain half-life. This half-life is a natural constant. It doesn't change. It doesn't change. This half-life is a natural constant. We know the half-life of all the isotopes, right? This big red book you see up there, I can actually show you. If I look up, let's see where it is, nuclear, most likely. (1156). Okay. If you look into big books like this, there are tables upon tables upon tables of half-lives of isotopes. Okay, all of this is known to great certainty. Lots and lots and lots of research was done to I love this book, by the way. Lots and lots of research was done to determine the half-life of all those different isotopes. That's a natural constant. We know the half-life. What you also know is that an isotope always decays along a certain chain, what we call a decay chain. For example, 232 thorium, right, decays in alpha decay to 228 radium, that decays in beta decay to 228 actinium, that decays in beta decay to 228 thorium, that decays in alpha decay to 224 radium, and so on, until we reach 208 lead. Okay, that's a certain decay chain, and it's always the same. Okay, it not suddenly decays in another way, it always decays in the same way. So by knowing all of this, by knowing all the half-lives, by knowing all the decay chains, and by having really good measurement equipment, like mass spectrometers that can distinguish every single isotope on the world, like really fast. I might explain how a mass spectrometer works in another episode. We can determine the age of rocks and of fossils by doing that, right? By doing that, we have different time intervals where one specific isotope, based on its half-life, works good, and then we piece all of them together, right? We don't want to rely on a single one, we piece different ones together and get all of the measurements, and then we have an interval, right? We won't get the exact same value, but what we get is a certain interval, the green one, a certain interval, and that is the possible age of our rock. It's somewhere between here and here. And that's exactly what scientists put in their publications. They say, okay, this rock is 4.5 billion years plus minus 100 million or so, right? And the error gets smaller if the rock isn't that old. However, it's important to note, you have to keep the rules in mind. If you add fresh kernels or remove popped kernels while the popping process is still at work, right? While it's still popping, you cannot do the calculations anymore. Same is true for rocks. For example, basalt. Okay, basalt is formed. It's a volcanic rock. It's formed out of lava. Okay, as long as it's molten, there is an exchange of the isotopes in the rock and the isotopes in the lava. So as long as this is happening, you cannot say anything about it. But as soon as it is cooled down, as soon as there is no more exchange, the clock begins to tick. And then you can use this method. However, it's really important that you study the rock really closely, because there are certain things that can happen to the rock that can remove certain isotope or add other isotopes, right? It can be partially molten again for some reason, right? There could be another volcanic eruption, and then lava is flowing over the surface of the old rock, right? So we have like rock number 1, and then we have lava flowing on top of it, and then we get like a zone. Okay, that's the old rock, the red one, and then we have lava flowing above it, and then we have this zone where the old rock is partially molten again. So if you take one of those rocks and you want to know how old is it, you do not take it from this top layer, right? Because you know this top layer has been alterated. And you have to document. You have to document whatever you're doing with the rock, okay? You have to document exactly where you take it, how you take it. You have to document what you're doing with it exactly, or people don't know whether or not they can trust your measurements, right? That's a problem with a lot of creationist scientists, right? They don't document this stuff. They take a rock and they don't, say, where did you take it, what happened to the rock in the geological history and so on. That could alter your results, or could influence your results. Another thing that creationists say often is that we use the C14 method on living animals and we got 80,000 years. That cannot be true. The C14 method doesn't work. Well, the thing is, C14 is constantly created in our atmosphere. Okay, so if we are constantly taking C14 in with the food we eat, with the water we drink, with the air we breathe. So the concentration changes. You're permanently adding new kernels to your bag. So those calculations don't work anymore. My name has been Mad Max. Thanks for watching, and tune in next time when I will talk about the history of the Earth.